Okay, so I'm going to talk you through some examples of proof. So here goes. So direct proof from 2018. Prove directly that the sum of any three consecutive integers is divisible by 3. Okay, so I am just going to pick three integers. So let's say A will go for n plus 1, and n plus 2, all integers. So where n is an integer. Okay, so I'm going to add them together. So n plus 1 plus n plus 2. That gives you 3n plus 3. You can take a common factor of 3 out. 3n plus 1, and this is divisible by 3. Okay, so you've proved that one. Part B. Prove that any odd integer can be expressed as a sum of two consecutive integers. Okay, so I'm going to say that if n is odd, then n must equal 2k plus 1. So let me pick two numbers. Let's go for, well, k being a number, and the next one up is k plus 1, and if you add them together, that gives you 2k plus 1, which is odd. So there we go. Okay, 2015 question 12. Prove that the difference between the squares of any two consecutive odd numbers is divisible by 8. You can choose any two odd numbers. I've picked, we'll go for n equals 2k plus 1, and we'll go for, say, p equals 2k plus 3, because I've kept it odd. Obviously, even adding odd's odd. So n squared, what we'll do is I'm going to start with the bigger of the 3. So the difference, p squared take away n squared, that is 2k plus 3 squared, take away 2k plus 1 squared, that gives you 4k squared plus 12k plus 9, take away 4k squared plus 4k plus 1. Hopefully you're getting to see it here. Well, that is going to cancel. I'm left with 12 take away 4, which is 8k, and 9 take away 1, which is 8. Again, like the first one, that's got a common factor, and therefore divisible by 8. So that's some direct proof examples. We're now going to have a look at proof by counter example. So for each of the following statements, decide whether it's true or false. If true, give a proof. If false, give a counter example. So I think that the top one is definitely false, and we're going to prove that the second one is actually true. So part A. So if a positive integer p is prime and so is 2p plus 1, right? Let's just start with the prime numbers and we'll keep going up. We're going to expect one of these not to work. So p equals 2. That's going to give you 2 lots of 2 plus 1 is 5, which is prime. Okay, so that works. What about p equals 3? Well, 2 lots of 3 plus 1 is 7, which is also prime. P equals 5. 2 lots of 5. Oops, not 5. 2 lots of 5 plus 1 equals 11. That is prime. P equals 7, next prime number. 2 lots of 7 plus 1. That is 15. That is not prime. So our counter example is not true for p equals 7. So that's our counter example. Okay, statement B, if a positive integer n has remainder 1, then when it's divided by 3, then n cubed also has a remainder 1 when divided by 3. Now, for statement B, if we are taking a number n and it's got a remainder 1 when divided by 3, we can write it as a multiple of 3 plus 1. This is just really a bit of algebra. I'm going to prove this is true. N cubed is 3k plus 1 cubed. So what's that going to be? So we'll start 3k plus 1, and that's going to be 9k squared plus 6k plus 1. Some old school nat 5 stuff here. That's 27k cubed plus 18k squared plus 3k plus 9k squared plus 6k plus 1. Simplifying that, 27k cubed plus 27k squared plus 9k plus 1. And what I want to show is that this is divisible by 3. It has got a remainder of 1 at the end. How are we going to show this is divisible by 3? Well, each of these numbers here, all in the 3 times table, 27, 27, and 9. You can, I'm just going to take a common factor of 3 out, so it's going to be 9k squared plus 9k plus 3. Sorry, squared plus 3k plus 1. You could have taken 9 out, but obviously 9 is still divisible by 3. And then you can say, well, you've proven it. Therefore, proven. Because what we could do is we could say, let 9k squared plus 9k cubed plus 9k squared plus 3k equal, I don't know, m. And then we could write that essentially as 3m plus 1, which has a remainder of 1 when divided by 3. Exactly the same form as the thing we started off with. Okay, right, proof by contradiction. Prove that if n squared is odd, then n squared plus 1 is even. So what we want to do is we are going to assume that n squared plus 1 is odd. Okay? So we're going to say that n being odd implies that n squared plus 1 is odd, and we are going to basically prove there's a contradiction. So I'm going to start off by saying, okay, well, if n squared plus 1 is odd, then I can write n squared plus 1 as an even number plus 1. Okay, then I'm going to compare that. Well, that means that n squared must be 2k. Well, 2 times any number is even, so that must mean that n squared is even, which means that n is also even. I'm going to put in imply symbols here, hopefully I'm using them right. Okay, well, there's your contradiction, because we stated at the start that n was odd. So what I'm going to write to finish off, I'll just change the colour. What we're going to write to finish off is contradiction. So n squared plus 1 is not odd, which implies that n squared plus 1 is even as required, and you can put a wee box at the end to show that you've completed your proof. Okay. 2010, question 12, prove by contradiction that if x is an irrational number, basically means it can be expressed as a fraction, then 2 plus x is irrational. So again, I am going to assume that x irrational implies that 2 plus x is rational. Okay, I'm going to basically prove this wrong. So, well, what does it mean if x is, if 2 plus x is rational? if 2 plus x is rational, means you can write it as a fraction, so a over b. Okay, so 2 plus x can be written as a over b. A and b are just integers, just positive numbers, and we're going to say that they're in its simplest form, so simplest form. So, well, I basically want to show that x is irrational. So x equals a over b minus 2, which can be written as, so if we write that as over 1, that's going to be a minus 2b over b. And again, do you know what, we could say that a minus 2b, if we let that equals c, what we can see here, what we've managed to do is write x as something divided by something else. They're all integers. That means that x is rational. So we have shown, so we've shown that x is rational. This is a contradiction. Therefore, x must, not x must be irrational. 2 plus x is irrational. Okay, right, proof by contrapositive. Now, the big thing for a contrapositive statement is, the thing I'm going to draw in a bubble here, probably should have drawn it, then the bubble around it, it is if P implies Q, then the contrapositive, let me just take that in, the contrapositive states not Q implies not P, so you're going to negate it. So for this one, what does that mean? Well, we are going to say that, well, x is odd, the negation of that is x is not odd, which means x is even. That implies that 6x plus 1 is not even, which means it is odd. Okay, so, well, let me start off. If x is even, means that x equals 2 times something. Okay, that's the way you can write an even number. Okay, well then, 6x plus 1 equals 6 lots of 2k plus 1. That is 12k plus 1, which is odd. So, which is odd. So what we need to state at the bottom, quite important, look at the marking schemes, that you need to say the contrapositive is true, therefore the original statement is true. Okay. Second last question, 2017, let n be an integer using proof by contrapositive. Show that if n squared is even, then n is even. Okay, so my contrapositive is going to be that I want to basically reverse them and say not. So n is not even, which means n is odd, implies that n squared is not even, which means n squared is odd. So if n is odd, n can be written as 2k plus 1. That means that n squared is 2k plus 1 squared. What I'm going to do there, oops, sorry. What I'm going to do there is multiply it out. That is 4k squared plus 4k plus 1. Now how am I going to show this as odd? Well, I want to show that this bit, first bit is even. Well, that is 2 lots of, in fact, make it 4, because 4 is an even number. 4 lots of k squared plus k plus 1. This yellow bit is even, plus an odd is always odd. So again, you could say the contrapositive is true, therefore the original statement is true. Okay, to finish off, 2019, we've got a couple of bits here. It says let n be a positive integer, find a counterexample to show that the following statement is false. Well, okay, let's see what we can pick. Having a wee look there, well, again, you could just go through numbers. Let's try n equals 1. What is that going to give us? N squared plus n plus 1. 1 squared plus 1 is 2 plus 1 is 3. Okay, that's not going to work. So, no. Yeah, in fact, yes, that's prime, so that holds, that's prime. Okay, if I put 2 in there, I'm going to get 2 squared plus 2, which is 6. Add 1 is 7, not 3. 3 squared is 9, plus 3 is 12, plus 1 is 13, that works. It comes out that n equals 4 is going to give you n squared plus n plus 1. What's that? 4 squared is 16, add 4 is 20, add 1 is 21. That is not prime. So there is your counterexample. Other numbers that would work, n equals 7 is another one, because that would give you n squared plus n plus 1. That's 49, add 1, which is 50, add 7, which is 57. That is not prime, because it can be divided by 3. Likewise, that can be divided by 3 and 7. So, that is your first one. Part B, write down the contrapositive of this statement. Well, we've just looked at this, so the contrapositive, if n squared minus 2n plus 7 is even and n is odd, right, the contrapositive is not this one, implies not that bit. So actually I'm going to circle the even part as well. So n is not odd, well that means that n is even, implies n squared minus 2n is even, well n squared minus 2n plus 7 is odd. And that's what you need for that one. Part B, I'm now going to use the contrapositive to prove that this statement holds. Okay, if n is even, then n equals 2k. That then means that n squared minus 2n plus 7 equals 2k squared minus 2k plus 7. We want to show that this is odd. Again, okay, that is going to be 4k squared minus 4k plus 7. And again, that is 4k squared minus k plus 7. This bit here is even, and again, if you've got an odd number, even plus odd is always odd. But again, to get your full marks, you then say the contrapositive, so not therefore, sorry, since the contrapositive is true, the original statement is also true. Okay.